Ballesteros, and this is my Physics 2211 Lab 2 motion of a falling object. The purpose of this experiment is to see the effect of drag on a dropped object in freefall. The results are that the drag causes an object to fall, quote, slower, meaning it covers less distance in the same amount of time. The principles for this lab are that for a falling object, the only forces acting on the ball are gravity and drag. These forces are unbalanced, meaning that they do not cancel and there is acceleration. We use Newton's second law, which shows that force is equal to mass times acceleration, and we look at the net force, which is the force of drag minus the force of gravity. When the force of gravity is larger than the force of drag, the object will have a net force acting on it and will be accelerating. When the force of gravity is equal to the force of drag, there is no net force acting on the object. Therefore, it will move at a constant velocity, which is called terminal velocity. We still use the velocity and position update formulas from Newton's law. The force due to gravity is negative mass times gravity, where gravity is 9.81 meters per second squared, and the drag force is negative b times the instantaneous velocity squared. The diagram of drag and gravity force illustrates these concepts. The key assumptions are that the drag force is always proportional to the square of the velocity. The force of gravity is constant and equal to negative 9.8 meters per second squared. For the lab setup, I chose to use a pickleball ball dropped from my hand as my system and everything else as the surroundings. I recorded the ball being dropped and tracked the motion using tracker software to create a position versus time graph of the ball from the initial time of 0. I then used GLOWSCRIPT to produce the computational model for the ball's motion. Using both sets of data, I created a comprehensive graph comparing both models of motion. For my calculations, the mass was 0.02211 kilograms, the diameter was 0.074 meters, the initial position was at y equals 0, the initial velocity was 0 because it was started at rest, the final observed time was 0.6 seconds, and I recorded the video at 30 frames per second. Here's the video of the ball being dropped. For my tracker data, I positioned the origin of the coordinate plane at the center of the ball in the first frame. The ball traveled along the negative y-axis as it fell to the floor. I trimmed the video to only have it during its fall without any bounce. For my GLOWSCRIPT code, I adjusted the net force calculations and implemented the velocity and position update formulas. I also accounted for the force of gravity and the force of drag. And this GLOWSCRIPT code was for the no drag scenario. As you can see, b equals 0. Here were my GLOWSCRIPT results for no drag. Acceleration was constant at negative 9.8 meters per second squared, and the ball will not reach terminal velocity. For the results with drag, I changed the b-value in GLOWSCRIPT to 0.004 so that the endpoint of my model was the same as my observed data. Here the net force is not constant, and F-net was found by using F-drag minus the force of gravity. The change in velocity was not consistent. Terminal velocity is possible in this scenario, although it was not reached. For comparing the models, as you can see in the model with no drag, it moved, quote, faster in that it covered more distance in less time. The tracker in the model with drag ended at the same endpoint, but moved hypothetically slower. Although the tracker and the computational model with drag were not the same, this may be due to inconsistencies in tracking or air resistance. What if, and what does this mean? The model with drag could predict that a terminal velocity because the drag force could balance out the force of gravity, meaning that there would be a net force of 0. If the object was thrown downward and not dropped, the terminal velocity depends on the velocity for the drag force being equal and opposite to its weight. The starting velocity is irrelevant because it can still reach the terminal velocity, which is not dependent on its initial velocity. It may reach this velocity faster, but the value will still remain the same. It depends on the forces, not the initial conditions. Terminal velocity is the speed at which they balance out, which does not change based on the starting speed. Thanks for watching.